Boomtown. All right. What are the derivatives of inverse trig functions? These are pretty much the last derivatives that you need to ever like to know for this class. We've pretty much done every other possible derivative. This is the last one that we really need to know for this class. And even then, I'll talk more about that as we get there. So today we're learning to find derivatives of inverse trig functions and use inverse trig functions. Yeah, so find derivatives of inverse trig functions and use inverse trig functions. So part of today is not just the knowing what the derivatives are, but using the derivatives. Or I'm sorry, let me rephrase how I said that. So when it comes to inverse trig functions, it's not just the knowing what their derivatives are, but also knowing how to use the inverse derivatives or inverse trig functions themselves. Because there's a couple extra things we're going to do with those. So I'll show you what I mean. And we'll jump at it. Yeah. All right. So this is just a general thing, which again, the more you reflect, kind of pun intended, on inverses, it makes sense. Like a trig function takes an angle and generates a ratio. An inverse trig function takes a ratio and gives you an angle, which makes sense because inverses undo the original function. That's the whole idea of inverses. And also reflection was a pun because we talk about if you take the line y equals x, you can reflect a function over that, and that should give you the inverse. So things are way less funny when I explain it, but I felt like I had to just to put that out there because I feel like that's a Friday sort of thing to do. But again, that's the idea behind pretty much everything we do is that whole idea of inverses, that they undo stuff. So they should undo things in the opposite order. So an angle to a ratio to an angle. Okay, so here are our inverse trig functions. I don't expect you to write them down. If you really want to write them down, again, there's graphs over here too. If you want to write them down, leave space and copy it out of the book. Yeah, if you really want to copy them, leave some space, move on. It's not super important to know these things. It's more be able to reference them and understand that the domain, or most of the stuff you need to know about the inverses are things that we did last year in pre-calc. Like their domain is the range of the original function. Like the domain of like arcsine in particular is -1 to 1, which is the range of sine. By the way, when we do inverse functions, we're going to use arc cosine, arc sine, arc tangent, arc cotangent, arc secant, and arc cosecant. So you're going to see both that arc notation and the inverse notation. So like sine inverse with the -1. You will see both of those. As I mentioned in pre-calc, they aren't different. They're just different ways to write it. The best explanation of why the arc notation even exists is so that people don't confuse the inverse for sine and cosine or for trig functions with the reciprocal. Because again, -1 in certain contexts just says do the reciprocal.
So arc is like the inverse?
Yep.
Okay, it's just another way, right?
Yep. Yeah, literally arc sine is equivalent to inverse sine. It's just another way to write it. Again, I've spent over the years of teaching calculus at least an hour or two a year searching, trying to find a better explanation. And basically all I get is just so people don't have to use the superscript notation or they don't get confused with reciprocals. But there's a bunch of stuff there. Yeah.
What is the IFF mean?
Oh, if and only if.
Oh, okay.
Yeah.
Okay.
Yeah, it's not capitalized there. So
I was just confused.
you're right. Like normal, every time I write it, I always capitalize it, and there it wasn't. That's fair. That's an earlier picture that I took from something and I just never replaced it. Here is the more important thing. Here are all the derivatives. So I will give you a moment to write those down because these are the last derivative rules that we are going to talk about in this class. Yes, these are the last derivative rules we're going to talk about in this class. And part of the reason I'll just give you a minute to write them down real quick, and then I'll talk more. you're not done writing right now, that's okay. I'm not gonna move on just yet. As you're writing them down, I intentionally placed them this way in the table, not because I just copied it from somewhere else, but they're intentionally arranged. Look at column 1, look at column 2. One of the biggest things that people ask as soon as we introduce like the reciprocal trig functions, secant, cosecant, cotangent. Why are they paired up the way they are? That's kind of stupid and silly. I don't like that. Okay, that's fair. Here's an example of like why it's nice they're paired up the way they are. Arc sine, the derivative of arc sine, derivative of arc cosine. They are almost identical, except arc cosine has a negative on top. Arc tan, arc cotan, there's a negative on top for arc cotan. Arc secant, arc cosecant, there's a negative on arc cosecant. So again, like while some of those reciprocal things feel like they should be matched up in different ways, here's a way, because of the way they are, that works really nicely and fits nicely into the way we think about things. But the big idea here is they all have a particular pattern. Now, knowing these patterns are helpful. The one in particular you'll probably see the most is arctan, in particular finding the antiderivative of that, but that's what we'll talk about more on Monday. Because if you look at that, that looks really close to like a log function, doing an antiderivative, I mean. So that one will come up a bunch, but notice in each of these that we're taking the derivative with respect to x of a function in terms of u. Again, we're thinking that is in terms of chain rule, that there's some interior function that we have to deal with. So u prime is the derivative of that. Again, you could just put, I guess we just put u prime up there. You could, in theory, replace u prime with du over dx, but then it just feels maybe a little more unnecessary, but okay. So now, what I'd like to do, now that you have a handy dandy little list of all 6 of these, which really, if you just remember the pilots, sine, tangent, secant, all are positive, and the co-pilots are all negative. Really, you just have to remember 3 rules and just remember to make them negative for the respective ones. Anyways, okay. Oh, that was for a different thing. So here's a random thing that we use inverses for. So I want to evaluate tangent of arc cosine of -2/5. So in order to do this, remember, inverses give me a ratio, inverse like arc cosine takes a ratio and gives me an angle. So why don't we just draw the triangle that goes along with this? Boom. And I know it could be here, it could be over here. The reason I put it here is because arc cosine, inverse cosine, only gives me things in the first 2 quadrants. So it has to be right there. And it's negative. Since it's negative, that means this part's negative. I can label this triangle like this. I don't actually have to find this angle. I just have to make a triangle where that is the angle I'm referencing. Because my angle is to get a ratio. I don't need the angle. I just need the angle to exist, even if I don't know what the exact angle is. Well, in order to find tangent, tangent's opposite over adjacent. So I need to find this length. Again, just good old Pythagorean theorem. And now that I have that, tangent of arc cosine of -2/5, pow! I really enjoyed putting the pow in there, like a lot, is square root of 21 over -2. So you're gonna have a couple problems in like maybe 2 or 3 problems in the practice for this lesson that we have to do something like this. Draw the triangle of the interior thing first, label the triangle, and then find the ratio you're looking for. Let's do another one. I think this one has a variable in it. It does. All right, so given y equals arc sine of x, find cosine of y. So this feels kind of weird, but basically I'm starting with the inverse. Let's draw a triangle from that. Because remember, arc sine takes a ratio and gives me an angle. So y is really an angle. this right down here also helps inform me where I should draw it. This, I was given extra information that it should be in the first quadrant. Well, based on the fact that arc sine of x is equal, or y equals arc sine of x, I can label this triangle a little bit further. Because sine of this angle should equal x. Note this right here. If y equals arc sine of x, then sine of y must equal x. That's the nature of inverses. Like if I took the sine of both sides of this equation, sine and arc sine undo each other, so I'd just be left with x. Since I know sine of y equals x, that's why I can put y, x over 1. Now that I know two sides of the triangle, I can figure out cosine of y. I just have to solve for this third side. This third side is going to have a variable expression to it. So it's probably use Pythagorean theorem. It should be the square root of 1 minus x squared. And because of that, pow, we can say cosine of y equals the square root of 1 minus x squared. Doing pretty good on this. So something I want to mention. I'm not sure how you're feeling about this right now, but it kind of feels like, oh my God, this is kind of wild and crazy. Like even still presenting it like it for the 6th, 7th time, it still feels kind of like a lot. This doesn't come up tons on the AP test. It's mostly just using the derivative a couple times with the chain rule is what comes up on the AP test. And even then, like probably arcsine and arctangent are the two that are going to show up the most often. I remember a couple years ago, I spent some time going through like 3 or 4 or 5 AP tests. I don't know how many it was. It was a couple two tree. And like the inverses aren't on there a whole lot. They occasionally show up. So it's not like a huge thing you need to know. It's an important thing to know to kind of complete your set of knowledge, but it's not as important for doing well in the AP test, if you catch my drift. Now, the reason we did this one, as well as this previous thing, was to kind of show you why the derivatives of the inverses are what they are. Because they seem really random. Like a derivative of an inverse trig is an irrational expression. How the hell does that work? So why is that true? So this one is animated for if you want to go through this on your own, but I'm going to go through it. So why is this true? Well, arc sine of x is equal to y if and only if x equals sine of y. So let's start with x equals sine of y. If I take the derivative of both sides with respect to x, on the left-hand side, I get x. On the right-hand side, I get cosine of y times dy dx. Okay, anyone in the bookshelves? Cosine of y. I wonder if I can figure that out. That's what we literally just did on the last slide. If we draw that triangle that goes along with this, we get this triangle over here, again, from the previous one. So cosine of y really equals 1 minus x squared. Now, in a sense, we could just be done when we get right here, because we've solved for dy dx. But again, typically, it's nice if we can to solve explicitly for a variable. And while it didn't seem like we could, by using some geometry as well, we can come up with an algebraic expression for cosine of y. And that's why the derivative of arcsine is 1 over 1 minus x squared, or u prime over 1 minus u squared. Do you have to know that? No, but like a lot of things, I want you to know why the derivatives are what they are. Like the only derivatives that we really presented without proof, I actually don't really, I mean, we didn't really present any of the rules, product rule, quotient rule, chain rule, with proofs. They're in the book. The proofs are in the book. We just didn't go through them in class. But like power rule, we kind of did the proof in pre-calc. At the end of pre-calc, we also did the proof of why sine and cosine are what they are. But again, both of those, all three of those really are just using the definition of the derivative. We went and we showed why the derivative of natural log is what it is. We showed why the derivative of e to the x is what it is. And that pretty much covers all of our functions. And the other 4 trig functions are all using chain or quotient rule with sine and cosine is really all those are. So I want to make sure you understand like why these are what they are. And by understand, I mean, I want to show you. If you don't fully understand, you're like, oh man, that's a buttload of algebra. It is a buttload of algebra and a bit of geometry. But I just wanted to like demonstrate to you, these aren't things that we're just saying are true. Here's why they are true. That's it. There you go. So the first 5 of the practice are mostly just doing stuff with inverse trig. Okay. The last 8 are actually using the derivatives. And for those, you're just using chain rule a lot of time. It's like, what's the derivative of arc sine of 3x? Well, plug in 3x in the appropriate places, find its derivative, put it there. Again, there's some rules and book examples for the derivatives. They're helpful. You can just see them and follow them through. There isn't anything too wild or crazy. Otherwise, I would have put another 1 or 2 up here. But I'll gladly answer questions about them as we go. By the way, this pro tip, this first part of it, you may need to set up 2 triangles. I'm going to tell you right now, that's for number 41. Oh, geez. Where did my mouse go? There it is. Number 41 is the one that you need to set up 2 separate triangles for. All right. I'm telling you right now, set up 2 separate triangles for 41. Make a note on your paper right now. You'll need to set up 2 triangles, one for the left side, one for the right side. Make a note right now. Make a note right now. You need a triangle for the left side and the right side of 41. Make a note right now. You need a one for the left side and the right side. Make a note right now. Maybe it's important if I've said it 75 times. I'll gladly still help you with it, but I want you to make a note of it because it's something I want to share. Do I have examples? Nope, I didn't. We basically went through the examples for 7 through 41. 43 to 50, there's a bunch of examples in the book, but I'll gladly spend time and still talk about things with you. So